Hello, everyone. Welcome to MACSMIN 2024. Our last talk today will be by Professor Alexander Movchan from the Department of Mathematical Sciences in our University of Liverpool. Alexander will talk about modeling of waves in semi-infinite metamaterials clusters. Please, Alexander.
Thanks very much, Vitaly. So, waves are quite important in studies of structured materials. Waves can be acoustic, elastic, electromagnetic, and I'm going to talk about different classes today. But the main point is that the microstructure is important, and the title includes the word metamaterials. In connection with waves, the term metamaterials is attributed to Professor John Pentry, Imperial College, and he introduced this term. Of course, nowadays the term metamaterials is used in many different areas, and people sometimes mean different things by that. But in the context of this talk, when I use the term metamaterials, I mean microstructured designer system, which gives you desired dynamic response. So, for example, you would like to shield sound of certain frequency, route waves around some object, polarize the wave in a certain way. You want to do something, you set your target, you design the material that will do it. And often materials I'm talking about cannot be found in nature, but they can be manufactured. And of course, with the new technology involving 3D printing, this can be the case that these materials can be manufactured at different scales. So, two examples that you see on the first slide. For some reason, my mouse, I can see it here. Just a moment, maybe. Here we go. Here, there is an interface, and chiral metamaterial, I'm going to talk about it shortly. The chirality is different above and below the interface, and then if I apply force, it generates a wave propagating only one direction, very unusual. And you wouldn't see anything like that if the chirality is absent. Here, again, you have interface, and again, you have chiral material here, chiral material there, and but when I say chiral, I will explain it later. It's not the same as just handedness. It's more than that. It's dynamic chirality, physical chirality. And here, across the interface, you can turn the wave around. And here, it's linked to the dispersion, which leads at certain frequency to high anisotropy. Now, since I talk about clusters, basically the message is you have many obstacles. And suppose you have a practical problem when you have an array of 100,000 scatterers. So what do you do about it? Put it all in the computer? Some people do, believe it or not. And then well, they will sit for a week waiting for the result, probably will spend a lot of money. It will be good on research spent spreadsheet. But I'm not going to do that. So if you look at this wall, you can see a doubly periodic structure. And if you assume that the color is the same, obviously it's not the same here, but if it is the same, then I can say that there is an elementary cell, which is square cell. And I will reduce my problem to the elementary cell problem. That's the advantage of having a periodic structure. But in my case, for this talk, I mentioned semi-infinite clusters. So there will be a boundary. and then I will explain what to do when there is a boundary. Okay, but for the introduction, as you can see here, there are some examples of elastic structures, and this is the example of a structure which has negative Poisson's ratio. So typically, if you have a elastic rod, you pull it in the middle, it's going to shrink, and in this case, this negative Poisson's ratio, as you pull it, is going to expand. So as you can see in this case, the structure is not just continuous, it's a lattice, but at the junctions you will have rotations. And because of these rotations, it creates this interesting feature. Another structure which couples compressional and rotational motions, and one more as well. But in this case, this one is continuous with the resonator. This one is a lattice structure. Also, you can think about this as geometrically chiral systems, and of course, the geometrically chiral structures and chirality as handedness is very well known. But I'm going to also talk about systems which possess. Oops. Okay. Now, what do I do? Ah, it doesn't play. That's very interesting. Ah. So, as you can see, here I have 3 spinners. And of course, if you look at a single spinner, it just spins and stays in one place. Now, this is a cluster of 3 spinners. They're connected to each other. If you look at this cluster, it turns around as the system. So the question is, if you have this kind of spinners embedded in your system, how do they interact with each other? And well, of course they do. And these are some examples of periodic structures. In this case, that doubly periodic structures, which have spinners embedded in it. And what exactly does it mean? In this case, you can see the picture. Think of gyroscopes sitting on the plane and connected by elastic springs. And of course, in this case, we are not doing a real life experiment. It's a mathematical model, and we look at time harmonic regime, which simplifies things dramatically. And if you say, does time harmonic regime in nature? The answer is, well, no. And unless you play an instrument that you play a certain tune, and that's what you wanted to do, to play this tune. But in reality, you have Fourier series. But from this Fourier series, you can always pick a term corresponding to a certain frequency, and then use that. But time harmonic regime is a very nice tool to analyze structures related to waves. Okay, and what happens is gyroscope is a frequency splitter. So, for example, if I take a pendulum, and I know that the frequency of a pendulum is square root of g divided by L, where g is gravity and L is the arm of the pendulum. Very simple. Now, imagine that now I attach a spinner to that gyro pendulum. Instead of single equation, now I have a system, and there will be not one frequency, but 2 frequencies. So every gyroscope is a frequency splitter. Therefore, when you look at your dispersion diagram, instead of one dispersion curve for scalar problem, dispersion surface, there will be 2 dispersion surfaces. So then, what else? Now, I would like to look further and mention this dynamic anisotropy. I'm not going to give you a detailed lecture about dynamic anisotropy, but anisotropy simply means that if you have material, the properties will be different if you point in different directions. And in this case, if you say take triangular lattice and homogenize it and consider this as static system, it will be isotropic. But as soon as you look at waves propagating in a lattice like this, and in this case, what happens is there are rotational elements embedded into this lattice, then you see this dynamic anisotropy. In particular, if I have spinners embedded in the left and right part, and I look at my dispersion relations, I can see that I can identify very strong anisotropy. And then I can use this anisotropy to create this kind of mode. So then I already mentioned picture like that. Here you have two half planes and gyroscopic lattice above and below, and different chirality, or we use the term gyristy. And in this case, if you apply a force on the interface, you will generate a one-way wave. In this case, it doesn't happen at any frequency. It happens at a particular frequency. And we refer to this as the so-called stop band. And at the upper edge of this stop band, you generate a wave in one direction. So that's the lower edge. In the at the upper edge, you have wave propagating in the other direction. And in physics, people use the term topologically protected structures. But of course, in that case, normally they refer to systems involving electromagnetic waves. And instead of gyroscope, they have a magnetic field of constant magnitude and direction. So that's what it is. Oops. Okay, now let me go to the next one. And now I wanted to show you what to do with the structures when there are many of them. With the scatterers when there are many of them, but it's not a periodic system. It has a boundary. So if it has a boundary, what can I do? I can't really take the elementary cell, and it's a big deal. And if you say, oh, I'm going to just use my solution for the semi-infinite problem, you can, but you have to know how, and I will explain how to do it. And there are different tools, and of course, one of the important tools is to use the so-called fundamental solution, or Green's kernel, Green's function. So it's related to point source. And in this case, it's an elementary example. Think of this table being semi-infinite in that direction. Okay, and then what I do, I say I'm going to nail that part of the table to the rigid foundation. Okay, and I have semi-infinite array of nails. Can you see these nails? Right. Yeah, here we go. Now, and then what I want is to send a wave. Here there are two pictures. One is when I have just a semi-infinite grating, and here when I have a semi-infinite half plane. So what do you do next? Well, you can say it's completely nailed to rigid foundation. Most likely it's going to just reflect the wave. And the answer is no. It depends on the angle of incidence, depends on the frequency. And so let me explain how it works. Mathematically, this problem is more challenging compared to the problem about the periodic system where you can just identify elementary cell. Right, okay, now have to go to the next slide. So first, in this case, I mentioned the flexural plate. So that's the operator. It's delta squared. That's delta is Laplacian. This is biharmonic operator. And that's operator of order 4 for the flexural plate. Beta is the spectral parameter, and it's proportional to square root of omega, where omega is the radiant frequency, and G is my Green's function, and here it's written explicitly. And H naught is the Hankel function, and K naught is the modified Bessel function. So this one is what you would see for standard Helmholtz equation, but this one is a special feature for the flexural waves. They're both singular, but they cancel each other's singularity. And this one is exponentially localized. Okay. So then what I can do is to look at my scattered field in that form, which is the input from every scatterer, which I model as a source. And these intensities are unknown. So here, the method uses the so-called functional equations of the Wiener-Hopf type. And the idea is that the Green's function is essential. So if you have Green's function, then you can do quite a lot. As you can see, it's not a lattice. It's a plate. But because I know the fundamental solution, I know G, I can write a very simple relation. And here you have, this is your incident wave, this is your scattered wave, that's the result, that's the resulting magnitude at the points which you have identified. And what I do, here I say I can take any integer n, but you say you have only pins applied on a semi-infinite line. But what I will do, I will mark integer points on the other semi-infinite line. So very good. Therefore, I do this. I multiply it by z to the n and take the sum over n from minus to plus infinity. Z is complex, and it's known as the Z transform. So if you know Fourier transform, it's very similar. And then, after we've done it, I always lose my mouse. I can write the equation in that form, where F is linked to the transform of my incident wave, B is linked to my resulting wave, and A and K are, A is this, and K is what I call the kernel function. And as you can see, this kernel function represents the so-called quasiperiodic Green's function that you would have for infinite array. That's where the connection is. So my problem is semi-infinite, but the kernel function of this equation is pretty much linked to the Green's function for the infinite periodic array. If you take z on the unit circle, that will be e to the I theta. Okay, you just use the Euler's representation. So it's a point on the unit circle. This is the Floquet factor, the phase shift related to the change from one cell to another. Then there is a procedure, and maybe I shouldn't go through this in great detail, but it's so-called Wiener-Hopf factorization. It's typical for problems related to on semi-infinite intervals. And as you can see, the equation can originally be written on the unit circle, where z has the modulus 1. But now I extended it into a ring, and then what I do, I then factorize my kernel into the functions which are analytic inside and outside. And this ring is the common origin of analyticity. And then for scalar problem, it's standard. If you have matrix problem, it's not always straightforward, but in this case, here we have scalar problem, so it's easy. And again, I lost my mouse. So then, what you do, this allows you to see what happens near the boundary. So, okay, just a moment. I lost it. No, here. So here, that's the boundary, and in this case, there are three different frequency regimes, and you can see the value for the spectral parameter. In particular, for the case when beta is equal to pi, as you can see, reflection is negligibly small. So it's a regime where this grating acts like a waveguide. So it pretty much takes your wave and carries it along. But the message is, if you look at wave problems like that, and in particular, it's applicable to scattering. If you look at the scattering pattern on a crystal, small perturbation of frequency of the wave that you use may be very, very important. So if you change beta just a tiny bit, can you see that's 3.1 or 3.3? And the reflection is quite significant, and that's your end region. And of course, you obtain this solution from the analysis of the functional equation of the Wiener-Hopf type. So, okay. Then, this is just the illustration where you can look at oblique incidence and look at shadow boundaries. So this is your shadow boundary. And again, you can do it using this method. And if you just want to look at the solution of the problem in the infinite periodic system, well, okay. It will give you some hints in the sense that you will have your Green's function for the infinite periodic structure, the quasiperiodic Green's function. But here we use this Green's function in the construction of the kernel of the equation. Right. So if I look at not a single grating, but a half plane, like I have described before, the structure is similar. But now my Green's function is linked to the plane. Okay. And in one direction, I have full periodicity in the transverse direction, and in one direction, I have a semi-infinite cluster. But as you can see, I have Hankel function, and I have the modified Bessel function K0, which is exponentially localized. They're both singular, and they cancel each other's singularity. But this one represents propagating outgoing wave. This one is evanescent. The same thing as before, but look, now I don't have just a single grating. I have infinite extent of gratings, but in the transverse direction. This is fine. And again, my Green's function now is different. It's a Green's function which represents the this function k. It represents doubly periodic structure, not periodic in one direction, but doubly periodic structure. So for the system like that, what do? How do you manage the computations? Imagine you want to do experiments with these things. It's a dead end. Many people tried to test structures like that and see how it reflects, how it transmits the wave, are there any trapped modes, and they usually spend hours, days, months, and they have a lot of data, and they find it inconclusive. Very difficult to sort out. Why? Because the system is very sensitive. And this approach gives you an analytical tool where you can see what happens if you change the frequency. So in a sense, if you run your experiments, you can design your experiments, you can say exactly where the interesting features are going to be. So that's the advantage of this. That's the advantage of this tool. So, for example, here I look at a diagram which can be interpreted as the projection of the dispersion surface to the kx, ky plane, where kx, ky are components of the wave vector. And sometimes this structure is called structure of so-called slowness surfaces. And in particular, here you can see so-called light cones. That's the terminology used by physicists. And if you would like interpretation, each of them represents the state of local neutrality. So if I choose my kx, ky corresponding to the vertex of the light cone, this will give me direction of special wave. In this case, I also have to tune the frequency corresponding to the vertex of this cone. And if I send that wave, this wave will propagate through the cluster, believe it or not, unperturbed, or the perturbation is going to be very, very small. And here we go. Look at that. So in this particular case, this is my wave, and it propagates. Sorry, not that one. That one. As you can see, reflection is pretty small, and it propagates pretty much unperturbed. And well, to guess this or to try in the experiment, you may be very, very close. But if your frequency is not exactly at the right value, you may just miss it. But the model here gives you exactly the method. So this is another example, and here you can say, how is it possible? Think of sending a wave with the nodal points exactly at the points where the pins are. So in a sense, nodal points are the points where the displacements are zero. Therefore, these spins are unperturbed. They don't produce any force. They don't produce any scattering. It's a very simple argument. But here you get it as a result of analytical model. So that's the message. You can do the same for oblique incidence, and this graph represents two methods. One is Wiener-Hopf, another one is so-called foldy, where you can truncate the series and reduce it to an algebraic system. But Wiener-Hopf is the best option when you want to look at the neighborhood of the boundary. for the neutral propagation, both methods give similar result. As you can see, this is your oblique incidence at the angle of pi/4, and it pretty much looks like nothing is there. No scatterers. Now, I already mentioned dynamic anisotropy, and this is just the slide which tells you how to analyze these direct cones. For this, you only need this quasiperiodic Green's function or the kernel function. The kernel function is really important. And finally, another example which is really simple, can't be simpler. And in this case, you have just two semi-infinite gratings. Can you see one and the second grating? And suppose you send a plane wave, and again, it's a flexural plate, and you say, is it going to trap this signal and guide it through, or is it going to block it and nothing is going to be inside? Very simple question. So now in this plate, I just make two semi-infinite rows, and I send the wave, and I want to know if this semi-infinite channel will absorb some of the wave or will simply stop it, and nothing will propagate inside. So similar formulation, exactly as before, but now I have two gratings, and the problem is symmetric, so I'm sending only the plane wave along the x-axis. So it's the same equation, delta squared, that's my biharmonic operator, beta is my spectral parameter, u is the flexural displacement, that's out of plane displacement. And my displacement is represented as the sum of the incident field, which is plane wave, and the scattered field. And the scattered field is the sum of two sources, okay? And I do have symmetry. Um are unknown amplitudes, and the summation m is along this semi-infinite double grating. G is the same as before. That's my Green's function in the time harmonic regime. Okay, these amplitudes um are unknown. Now, as before, here I can take the Z transform. I can arrange the equation in this form, which is my functional equation of the Wiener-Hopf type. And K is my kernel function written here. Okay. So the analysis of this kernel function, again, allows me to look at transmission and reflection regimes. And this is the example of trapped wave. As you can see, the wave is trapped inside, and A is the total field, and B is specifically the scattered field. So you can see how it works. Now I'm looking at different value of the spectral parameter. And what I see is, again, I have trapped wave, but this period is different. So, and you can see I have two modes. I have the envelope mode and rapid oscillations, and this can be quite tricky. So if you try to use your intuition, it doesn't work. But the analytical model does. So in a sense, if I take my kernel and even without solving the Wiener-Hopf equation as such, I can simply say, let me look at the magnitude of my kernel function evaluated at e to the ika. A is the distance between the pins, and I can see the zeros, and the frequencies of oscillation and the envelope they can be identified according to this zeros, which is great. And finally, I can also derive a homogenization model for the waveguide and derive this pretty simple dispersion equation where I can write beta as a function of k, and it works really well. Okay. So now that was the technical part, and finally I thought I'll just mention a few other things, but I'll show the pictures and references. So if you look into chiral systems, and by chiral systems I explained these are dynamic chiral systems where you have gyroscopic force, and of course I already mentioned the Floquet pendulum. And Floquet pendulum is the best example to see the chiral system which possesses this gyroscopic property. You can say there's no gyroscope there; it's just a pendulum, but it's Coriolis force. And what happens is when it moves, Coriolis force, as the pendulum moves this way, pushes it to the right. If you go to the chemistry building where the Floquet pendulum is, look at how it moves. It moves like a normal pendulum, but in addition, it drifts in the clockwise direction. In this case, here you have a lattice with many gyroscopes embedded. And so in the governing equations, you simply have this gyroscopic force, which is orthogonal to the velocity vector. And then at every interface, here you change the juristy. So you change the direction of spin. And because it's up to you, you have control, then you have this problem. Now, because when you run the computations, you have to do something at the boundary of the computational window. Here, we use so-called perfectly matched layers, absorbing layers. For the flexural plate, you have to program them. If you have Helmholtz, there are standard subroutines. But for flexural plate, it's quite straightforward to program them. But if you don't use perfectly matched layers and simply assume that there is no juristy here, well, you know, it will still give you the pattern, but maybe not sharp, not as sharp as with the perfectly matched layers. So it's a little computational problem. Now, there is another trick. If I simply take a force and start moving it around in a structure like that with two interfaces that cross each other, I will have a rhombus. But there is optimal size of this rhombus. So in a sense, instead, I can take a problem without any forcing and set it up to run so-called eigenvalue problem. So I will look for eigenvalues and corresponding eigenfunctions, and that's what it gives me. So in a sense, it's a resonance mode. And of course, if you apply the force here, you will see fairly high amplitude. A few papers. This one is in scientific reports deflecting elastic prism on highly anisotropic chiral structures. Then gyroelastic beams and vibration reduction for long flexural systems. So you can use gyroscopes to build bypass systems. And you can say, if it's such a simple idea, have people used it anywhere? The answer is yes. If you're in Tokyo, then go and have a look at the Skytree. Skytree is the television tower. The special thing about this tower is it doesn't shake, even during earthquakes. And the quality of television transmission is good. So it doesn't shake. You can say, how did they do it? Oh, they don't tell you. But what they've done is there is a gyroscopic core in the middle. And during earthquakes, it goes crazy. And of course, it works like a waveguide. And because it's gyroscopic, you can have a control over gyroicity. So basically, you increase or decrease the speed. Oh, they don't do it by hand. They have sensors. And therefore, instead of walls of the tower vibrating, this core vibrates. And of course, when it vibrates, they know where the energy goes, and they dissipate it. So they have shock absorbers. And, well, not springs, but they have viscous shock absorbers. So that's how it works. Skytree. If you are in Tokyo, go and have a look, especially during earthquake. Okay. So another paper, elastic chiral waveguides with gyro hinges. In this case, you have gyroscopes, but the conditions at periodic waveguide are such that the displacements are zero and moments are zero. So if it's a flexural beam, then there is no resistance to rotation. But if you stick a gyroscope, then of course it does provide resistance, but it's a gyroscopic resistance. It provides coupling between two transverse displacements. And then I think I have already mentioned that one. And then vibrations and elastic waves in chiral multistructures. So in this case, think of a beam, and on the top of the beam you have a mass. And of course the frequency will change. But now instead of this mass, say I'm going to put rotating body. So it has its own inertia, but in addition it rotates. And then it will start splitting frequencies of this beam. And of course, sometimes people talk about gyroscopic rigidity, and it's great. But there is another thing. In addition to high frequencies, it creates fairly low frequencies. And of course, experts who work on systems like that, they are aware of this. Most of the time, the gyroscopic rigidity corresponding to high frequencies is used. But for example, if you look at the way helicopters are operated, the helicopter blades, when you put them together, can be considered as a gyroscope. And when they start the engine, they really want to pass the regime corresponding to low resonance frequency very, very quickly. And when they shut it down, they have dampers. And these dampers are essential. If these dampers are out of order, the helicopter may be damaged. And you can even find on YouTube video with a Chinook helicopter being destroyed deliberately as part of the experiment. And this dampers were removed, and on shutdown, it picked up the low frequency resonance corresponding to this resonance for the gyroscope, and it's just gone. If you Google Chinook resonance, you will find it. And it wasn't an accident, it was a pre-designed experiment. And well, here we go. I'll stop here. Thanks.
Thank you. Thank you, Alexander. Let me thank Alexander for the talk. I'll stop recording.